Okay, so for today, we are going to talk about one of the greatest feuds ever in science. Okay, if you ever watched epic rap battles of history, there's actually an epic rap battle about Kepler and Tycho Brahe. Okay, so if you ever watched it, there is one for them. We can of course play it in this class because it's not appropriate, but okay, if you do watch that sort of thing, they do have one. It is a major feud, and it had to do with basically changing the way people thought, right, based on data. So at the time that Kepler kind of came to fame, we'll say, was still a time where most people, including scientists, thought that the Earth was the center of the universe and that everything orbited the Earth. Okay? Which of course it doesn't. If you think that, I'm going to open your eyes today to the real world, where no, not everything orbits the Earth. Okay? So Kepler he wasn't an astronomer. He wasn't anything like that. He was a mathematician, and he was hired by an astronomer. Okay? The astronomer's name was Tycho Brahe. Tycho Brahe was kind of nearing the end of his career. He was an older man, but he had spent his entire life watching the sky. He had made like copious observations, meticulous measurements and observations of the location of objects in the sky. And he believed wholeheartedly that the Earth was the center of the universe. The problem was his data didn't seem to support that belief. Okay? So he just figured, I must not be good enough at math to make my observations say what I want them to say, which is like the worst thing you can do in science. I don't like my observations. They don't say the right thing. So no, you make observations and they say what they say and you have to go with that. So what he did is he hired a mathematician, Kepler. Okay? Kepler had a very good reputation as being very good at math. Okay? Tycho Brahe handed over his life's work to Kepler and said, make it so that my observations say the Earth is the center of the universe. And Kepler went, okay, I mean, I need a job, so I'm going to work on this. Okay? The problem is, that's not what Tycho Brahe's data said. Okay? Tycho Brahe, even though he had faults, gathered meticulous data. The problem he had was this. When he observed Mars in particular, but a few other planets, move through the sky, they appeared to do something weird. Okay? So he would watch Mars move through the night sky over the course of months at a time. And every once in a while, Mars would stop moving forwards in the sky. And it would move backwards, and then move forwards again, and continue on. This is a strange thing. Okay? If Mars orbits the Earth, why in the heck would it stop, turn around, back up, stop, and then turn around and go forwards again? It didn't make sense from an orbital mechanics kind of perspective. Okay? So this is what he needed Kepler for. He actually found that most of the planets did this, at least at some point. Mars did it more often, because Mars and Earth are close together. Okay? So it didn't take Kepler very long, being a mathematician, to figure out what the problem was. And the problem was that the Earth was not the center of the universe. Okay? The only reason that Mars would appear to back up in its orbit is the same reason it looks like when you pass a car on the highway that car is moving backwards. Right? You're coming up on a car, it's clearly moving forwards, but as you pass it appears to fall behind you. And then when you get far enough ahead of it, you can tell that it's actually still moving forwards. Okay? So what was happening here was this is where Earth would pass Mars in its orbit, because Earth is inside of Mars's orbit. Okay? So as Earth would pass Mars, it would make Mars look like it was backing up. Okay? So Kepler figures this out like not very long into his data crunching. But he doesn't want to tell Brahe because he'll get fired. Okay? This is not the news Brahe wants to hear. Right? So he kind of keeps it from him and he studies all of his data. And in studying all of his data, he comes up with essentially all of the proof that the sun is the center of our solar system, using Tycho Brahe's life work. Okay? Eventually, Tycho Brahe is like, hey, come on, I've given you long enough. You're supposed to be good at math. What the heck? Why aren't you done this job? And Kepler says, well, I've actually been done for quite a while. You're not going to like it, but Earth is not the center of the universe. You're fired! Okay? I mean, he was enraged. Okay? And he wouldn't even listen to Kepler when Kepler tried to explain to him how good his data was and how well it proved that Earth was not the center of the universe. Okay? I mean, imagine, someone takes your whole life's work and uses it to make a fool of you. That's how he would have felt. Yeah. Okay? He would have felt like humiliated because his whole life he said the Earth's the center of the universe and I have all this meticulous data to prove it. Except he didn't. Okay? He had meticulous data that proved exactly the opposite. Right? So he promptly fired Kepler, who then went, oh yeah? Well, I am going to take all of your data and I'm going to use it to ruin you. Okay? Now, this is not a life lesson, this is not how you should behave, but okay? He went on to prove all the orbital mechanics as we know them in our solar system with Brahe's data. So you can imagine that Brahe went to his grave hating Kepler, okay? And still believing that the Earth was the center of the universe even though there was all this evidence against it. Right? So they had a feud that went on for years between them because of all of this. Okay? So here's what Kepler discovered using Brahe's data. And keep in mind that all of this happens before Newton figures out gravity. Okay? Kepler uses Brahe's data to figure out that everything orbits the sun with no understanding of the concept of the force of gravity. Okay? This is just watching things move in the sky over the course of 50 years. Okay? So, what Kepler discovers is that the planets, when they orbit the sun, don't go the same speed. And I don't mean that Earth moves faster than Mars. I mean Earth actually changes speed as it orbits the sun. Okay? Now, we know that if it's orbiting the sun, it has to obey this law. So if the speed is changing, what else must be changing? The centripetal force and or the radius. In fact, both. The only reason that Earth's speed should change is if it gets closer to the sun and the sun somehow pulls harder on it. Now remember, he didn't know about gravity, so all he knew was that the radius of the circle must be changing in order to make the speed change. So he said, not only does every planet in the solar system orbit the sun, but they don't orbit in a circle. They orbit in an ellipse. Okay? So a slightly flattened circle. So there are times of the year where Earth is further from the sun than others, and where it moves a little bit slower. Okay? And times where it's a little bit closer and moves a little bit faster. Okay? Kepler called this his law of elliptical orbits. Okay? So what effect does that have on us? Our gut reactions go, seasons. The further away, it must be colder. Actually, not true. What causes the seasons?
Tilt.
The Earth's tilt. Okay? So, believe it or not, we're actually closest to the sun in winter. But we're tilted away from the sun. So as the Earth orbits the sun, okay, so we got the sun here, okay, and then we've got the Earth out here. So as Earth goes around the sun, okay, in its orbit, when it's here, okay, it's tilted, right, and here it's tilted, and here it's tilted, and here it's tilted. Okay, well, when it's tilted here, the tilt doesn't matter. One side faces the sun, one side faces away, and those are the days when there's an equal amount of daylight hours and an equal amount of nighttime hours. What do we call those days?
Equinox.
The equinoxes. Okay, so this would be the vernal equinox. Okay, and this would be the autumnal equinox. Okay, so March 21st and September 21st. Okay? What day of the year is this, where the North Pole is pointed at the sun? Pointed at the sun.
Oh.
The other one. June 21st. Okay? This is the summer solstice. Okay? In the northern hemisphere, that's the longest day of the year for us because the Earth's axis is pointed at the sun. So when the Earth rotates around its axis, we spend a lot more time in the sun. Okay? If you're at the North Pole or above the Arctic Circle, the sun doesn't set. Okay? You can actually watch it move in a circle around you, okay, on the summer solstice. Okay? This, okay, we're still tilted the same way, but now it's December 21st. So we're coming up on this one, shortest day of the year. Okay? Because now as we rotate around, we spend very little time in the sun because we're pointed away from it. Right? We'll get that 6 hours of sunlight day on December 21st. Okay? So that's the winter solstice. Okay? So that's what causes the seasons. It's actually the tilt of the Earth. Okay? But we actually are closer to the sun in winter. Now, I don't know if this has ever bothered you, but it used to like really bother me until I learned why it's true. You ever notice that not all the months are the same length? Right? And there doesn't seem to be a really good reason for that. It's like fairly random. It's like this month has 31 days. This month only has 30 days for whatever reason. February only has 28. Okay? Why? Does anyone know why?
Isn't it because like 2 months got, or is 2 months got added, right? By
Caesar changed the calendar,
oh.
From the like to the what do they call it? I can't remember the name. From the Gregorian calendar to whatever the other one was, but actually no. It's because the seasons aren't the same length. Because Earth moves at different speeds in its orbit. Winter is actually the shortest season. Okay? I mean, it goes through February, which is the shortest month, right? So it starts on December 21st, goes through January, right? Goes through that short month in February and only goes to March 21st. Okay? Spring and summer are our longest ones. Okay? They're over 90 days. Okay? It's because this is actually shifted a little bit to look more like this diagram here. Okay? That's greatly exaggerated, obviously. Earth does not get that close and that far from the sun, or we would sequentially freeze and fry, okay, if that actually happened. But, okay, there are times of the year where we're closer to the sun, so we move through a greater percentage of our orbit in the same amount of time. Okay? Everyone kind of with me there? Okay? So because we're sharing this, or because we're moving a little bit faster, we cover more of the part of the orbit where we're close. Okay? That also happens to be when we're pointed away from the sun in wintertime for us. Okay? All right, so Kepler's law of elliptical orbit says that the speed changes. I've observed that. And then he came up with this other idea called the law of equal areas, which explains this. Even though I move through more of the orbit, because the radius is smaller, this area is equal to this area. Let's say each one of those areas is a 30-day time period. Okay, so it's the same amount of time, but because the Earth is closer to the sun, it moves through more of the ellipse then in those 30 days than it does when it's further away. The areas are still equal, but we do represent different amounts of the circumference of that ellipse. Okay? Oh, I even had a diagram for that. Okay. Let's get that part. So, here's the logic. Winter is 89 days long. Unless it's a leap year, then it's 90. Okay? Autumn is 90 days long. Spring and summer are 93 and 94. Okay? Because during those seasons, we're further away and we're moving slower. Okay? So we're not covering as much of the total circumference of our orbit. Okay? So those seasons are longer. Thankfully, you're in the northern hemisphere. If it was the other way around, you'd have short summers and springs if it was in the southern hemisphere. Okay? Everybody with me there? All you're really going to need to know about Kepler is his 3 laws. Okay? And then you're going to be good. We're not going to do a lot of problem solving. Okay, so Kepler's first law, law of elliptical orbits. Everything moves in an ellipse. I know this because I've observed from Tycho Brahe's data that the speed of the planets change as they move. Okay? His second law is this law of equal areas. So this is a much better diagram than the one I just drew. Okay? So here, during the winter, okay, we move through this much of the orbit. That area and that area are equal, even though they represent different amounts of the circumference of the ellipse. Okay? Now, some planets have orbits that are more elliptical than others. Okay? And the more elliptical your orbit, the more exaggerated the effects of that are going to be. Okay? For Mercury, Mercury's orbit is actually quite elliptical. Okay? It's over 20% different when it's at its apogee. Okay? That's the furthest point, and it's perigee. That's its closest point. So this here is what we call perigee. Can't use blue on blue. Okay, and this is apogee. Okay, this is our furthest point. Okay, so Mercury is 20% closer at perigee than it is at apogee. That's a fairly elliptical orbit. Okay, Venus has an almost perfectly circular orbit. It's less than 1% different, apogee to perigee. Okay, Earth, just under 2% different. Okay? It's enough to make a difference. Okay? We can see that the length of our seasons is not equal, and that is based on how much closer Earth is, okay, at one point than the other. Mars, almost 10%. Okay? So it's quite elliptical compared to ours. Okay? And then you've got Ceres, that's an asteroid in the asteroid belt, about 8%. Jupiter, about 5%. Saturn, about 5%. Uranus, that's how you say it. We talked about that yesterday. Okay, about 5%. Neptune, almost a perfect circle. Okay, and then you've got your Kuiper belt objects. Okay, are their orbits highly elliptical? That's why they're not planets anymore. Okay, it is for this reason that Pluto is no longer a planet. Pluto does not dominate its orbit and does not actually orbit in the ecliptic plane. Okay? The ecliptic plane means that you can eclipse another planet. Okay? If we're looking at the sun being here, most of the planets orbit along that plane. Pluto does this. Okay? And it actually crosses Neptune's orbit and is closer than Neptune for part of its orbit. Okay? So it can't be a planet because it doesn't have its own orbital path. It doesn't cross another planet. And it's so elliptical that it actually becomes closer than another planet. So that's the reason they took it off. It has to dominate its orbit, and it doesn't. Neptune is bigger and in its orbit. Okay? Eris and Sedna, it was actually Eris that was the reason Pluto wasn't a planet anymore. It was the discovery of that body that caused us to kick Pluto out of the planet club. Okay? All right, making sense? So we got law of elliptical orbits. We know that because the speed changes. Law of equal areas is just kind of the proof of that, okay, seeing that it covers these different amounts and changes its speed, okay? And then the last law is the law of periods, which we'll get to in a minute. So, difference in speed for the Earth. When we're at perigee, the Earth moves at 109,289 kilometers per hour. That's fast. Earth is zipping along. Okay? But when we're at apogee, it's 3,000 kilometers an hour, more than 3,000 kilometers an hour slower. Okay? Almost 4,000. Okay? It makes a difference. Right? We don't cover as much of that circumference there as we do there. So we travel through more of our wintertime orbit, okay, in a shorter period of time. Okay, so those two things were fine. Kepler had those. But the real ace in the hole that he had was using Bray's data. He found out that all of the planets share a property if they orbit the sun. Okay? He found that if you take the period of any planet in the solar system, its orbital period around the sun, and square it, and then divide it by its orbital radius cubed, you get the same number. Doesn't matter whether you do that with Earth's numbers, Jupiter's numbers, Neptune's numbers, even Pluto's numbers. You get the same number. which he appropriately called Kepler's constant. Okay? Because it was the mathematical slap in the face to Tycho Brahe. The only reason all of these planets could possibly have that number in common is if they all have the same orbital center, the sun. Okay? This is also true for moons orbiting the same planet. If I did this with any of Jupiter's moons, I would get the same number for all of them. Okay? We can't really do that for Earth because we only have one moon, which makes it easy to name. You only have one moon, you can just call it the moon. Okay? It's a little different if you've got more than one. Okay? All right. Is that sort of making sense? Okay? So what Kepler discovered, and this actually got used later on, okay, was that you could use that to predict the orbital period or orbital radius of other planets. Okay? If you knew the numbers for Earth, then you could use them to extrapolate for other places in the solar system. So if we thought there might be a planet out at a certain distance, we would know the radius of that planet. We could use Earth's numbers here and predict what the orbital period of that planet would be, and then we'd know where to look for it. Okay? It's how we can predict where planets we can't see with the naked eye would be. It's how Uranus, Neptune, and Pluto were all discovered. Okay? We kind of predicted where they would be and aimed a telescope there and waited. All right. This making some sense? So, like I said, this works for moons as well, okay, as long as they have the same orbital center. Okay, so they have to be orbiting the same planet. All right. Trivia for you. Is there a naming scheme for moons?
Yes.
Yes. What is it?
It's the name of the planet and that's how we normally call it.
It is. Okay. So for Earth, we have Terra and Luna. Luna is actually the name of the moon. Okay. For Mars, which is the god of war, its two moons are Phobos and Deimos, the companions of war. Phobos is fear, Deimos is panic. Okay? So anything that, if we discover any more moons around Mars, they have to have a war theme to them. Okay? Jupiter is awful. Okay? Jupiter is the king of the gods, and all of its moons are named for the lovers of Zeus. There are 70. Okay? Not a nice guy. Okay? Yeah. There's a lot of moons. And we're not out of names, so yeah, okay, there's that to consider. For Saturn, they're all Titans. Okay, all of the moons of Saturn are Titans. Okay, for Uranus, they're all Shakespearean characters. For whatever reason. Okay, they're all Shakespearean characters, so like Puck and Miranda and all these things, like Midsummer Night's Dream and all those. Okay. For Neptune, they all have to have a marine theme because Neptune is the god of the sea. So you have Triton, the trident that he would carry, okay, and all the other moons have to have a theme around water. And for Pluto, it's all stuff for the underworld because Pluto was the god of the underworld. So we've got Charon, which is the person who mans the boat that takes you across the river Styx. Okay, one of them is called Styx, named for the river. Okay, and then you got a whole bunch of other ones that all have to do with the underworld. So there's actually a naming scheme. If you ever discover a moon, you can't just name it whatever you want. Okay, because reasons, I guess. Yeah. All right, there's some useless trivia for you. Okay, so I would say this stuff here that is highlighted, that should go in your notes. Okay, so I'll give it a few minutes, copy that down. Those are Kepler's 3 laws. That's an easy multiple choice question. Which of the following would Kepler not agree with? Okay, pick the one he doesn't agree with, 3 out of 4. Okay, I'll give you a minute on that one. Okay, so the extent to which you need to be familiar with Kepler is just to know these are his 3 laws. Okay, you got the law of elliptical orbits, the law of equal areas, and the law of periods. Okay, just be able to identify that in the multiple choice question. I'm not going to ask you to do any calculating. You're not required to calculate anything with this law of periods. Okay, or really do anything else. Okay, just know these are Kepler's laws. All right, next thing we got to talk about here is satellite motion. Okay, we actually did a satellite motion question yesterday when we calculated the speed of the moon as it moves through its orbit around the Earth. Okay, what we're going to look at today is kind of the idea behind how satellites work, and then how do we solve satellite motion problems. Okay, the good news is you solve every satellite motion problem the same way. What provides the centripetal force that keeps the satellite in orbit? Gravity. Okay, so anytime you have one object orbiting another, you know that this is true. Fc equals Fg. But it's big Fg. Okay, it's this. Okay, that is the basis for any satellite motion problem. Okay, as a quick review, yesterday we did a problem like this, and we found that one of the masses is on both sides. Which mass is on both sides? The orbiting body or the orbited body? The orbiting body. The one that's moving in a circle is the m that is in mv squared over r. Okay, so that means that the mass of the satellite is always going to cancel. Okay, and we'll look at why that is here a little bit today. Okay, so satellites obey uniform circular motion laws. They are not a vertical circle. Even if they have a polar orbit, okay, where they go over the North Pole and the South Pole, they are still a horizontal circle. Okay, there's no vertical aspect to that because gravity is affecting them exactly the same no matter where in the orbit they are. Okay, and obviously this thing we just talked about, understand that for all orbiting bodies, gravitational attraction between them is what provides the centripetal force. Okay, the last point there has been known since Newton's time, but it wasn't until the late 50s, early 60s, okay, that we were actually able to pull it off. Okay? The key to getting something to orbit something else is to ensure that the distance it falls towards the bigger body is accounted for by how much that body curves away. Because Earth's round. We might have covered that already. Okay? But it's essential for satellites to work, for the Earth to be round. Right? Okay? So this is the thing that Newton knew. Okay? If you wanted to get something to orbit something else, you had to make sure that it was going fast enough that the distance it fell was also the distance that that round body curved away. Because then it would never get any closer. Right? So Newton came up with this idea, and he ran one of his famous thought experiments. Okay? Where he didn't have the technology to make it work, but he ran it in his head. Okay? He said, if you put a cannon on top of a really high mountain, okay, and fire a cannonball, if you can get it to travel far enough, then the distance it will fall in the first second, which for any object would be 4.9 meters near the Earth's surface, if you can get it to fly far enough in that time, that's how far the Earth will curve away. Okay? Which means it never gets any closer to the center and the radius stays constant. And then it would orbit the Earth. Okay? So near the Earth's surface, if you're going to get the Earth to curve away 4.9 meters, you have to travel 8 kilometers along its surface in 1 second. Is that fast? Yeah. Can anything travel that fast within the Earth's atmosphere? It'll what? It'll burn up. Okay? I mean, we cannot make anything go that fast. It's why things burn up when they fall out of orbit. They're literally going that kind of fast. Okay? So, near the Earth's surface, this is effectively impossible. Okay? But if you could make that happen, don't stay on top of the mountain after you fire the cannon. Because it's going to come back around, okay, and get you from behind, okay, because it would actually orbit the Earth. Okay? So, we understood this. But we didn't get satellites into orbit until the late 50s, early 60s. Who got up there first? Yeah, the Sputnik was the first object, man-made object to orbit the Earth. Okay? It terrified people at the time. okay? Just like a little basketball with antennas coming off of it, okay? And it went beep, 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 and it terrified people, okay? Because if you could make that orbit the Earth, what else could you make orbit the Earth? Nuclear weapons. You have to, it was a different time, okay? People were afraid of different things, okay? But it was certainly, okay, something that terrified people, and they were the only country on Earth who'd been able to do it, right? Obviously, the space race started, and then things really got going, okay? But getting that something to orbit the Earth meant you had to make it go not only really fast, but also really high, okay? Because you can't get this kind of speed in the Earth's atmosphere. You have to be outside of the Earth's atmosphere, or whatever you're launching will just burn up. Okay? Now, Sputnik didn't last very long. It deorbited, okay, because it was in very low Earth orbit. But okay, we got better and better at it. Now we've got things that are way out, okay, in geosynchronous orbit even. Okay? The key is you had to have the technology to make things go really fast and get really high. You needed rockets, okay? And that was what got the whole space race going. Okay, so this was kind of Newton's idea. If you hit something but it didn't go far enough, it would follow a projectile arc back to the Earth, right? All projectiles are going to do that. If you hit it a little faster, okay, it's still going to follow a projectile arc. If you can get it to go fast enough, that projectile arc becomes a full circle, and then you've got something orbiting the Earth. Okay? Everybody all right with that idea? Okay, so a satellite in orbit is always going to be the same height above the Earth's surface. Radius has to be fixed unless you've got some sort of like really fancy spy satellite that you're moving around all over the place. Okay, but it's going to be staying in this one radius. Okay, so its centripetal acceleration would be v squared over r. Okay, so essentially what we do here is we say, okay, the centripetal acceleration is caused by gravity, so we can say what we said earlier. The centripetal force acting on a satellite is the gravitational attraction between the satellite and the Earth. Okay? Now, is it the Earth on the satellite, or is it mutual? It's mutual. It's really important to remember that. That universal law of gravitation specifically, explicitly states the attractive force is mutual between the two. All right, so what that means is big G times the mass of the Earth times the satellite over r squared equals mv squared over r. Okay, and then we could manipulate to find things like how fast the satellite is going, how far above the Earth's surface it is, okay, all of that kind of stuff. Now, this r and this r, same number? They are. They're the distance from the satellite to where? To the center of the Earth. That comes up as a trick constantly in satellite questions. You have to remember that when you're using Newton's universal law of gravitation, r is the center to center distance. Lots of times, a question will give you the altitude of the satellite. Where is that measured from?
Sea level.
From sea level, from the surface of the Earth. Okay, so that's not the whole distance then, is it? What would you have to add to that number? The radius of the Earth. Okay, if they tell you it's this at this altitude, you know you actually need that distance. So you would have to add on the radius of the Earth. The other way they can do that is they can flip it. And they can say, how far above the Earth's surface is this satellite? Well, you can't solve for that number directly. You can solve for this number and then subtract the radius of the Earth. It's just a little trick, but it comes up all the time. Okay? The reason little tricks like that come up all the time is because every satellite motion question ends up being this. FC equals FG. Okay? So you're just manipulating. The only way they can make them difficult is to throw little tricks in them like that. Okay. Something that's important for satellites. Obviously, speed is important. But something that we haven't talked about that is pretty important is this. What does big T stand for again? Period. Okay. Is the period of a satellite's orbit an important number? It is. But when we do this, period's not in there, is it? Okay, but I mean, if you were asked to solve, if you could solve for V, you'd already know R. Could you solve for it then? Right? You could do it in 2 steps. You could go right? Here's what sometimes happens. Sometimes a question will make it so that the givens you get make it impossible to do this in 2 steps. Okay? So what they might do is give you the orbital period of the satellite instead of its speed and ask you to calculate its radius. Now there's no way to do this in 2 steps. So you have to do something you learned how to do in math. Okay? If this equals V, this formula here, can I substitute it into this formula? I absolutely can. Okay? You will probably end up having to do a substitution with satellite motion where 2 pi r over t goes in for V. What's the trick here? In that formula, V is squared. So what do I have to do with that formula? I have to square it. Yeah. Okay? So if I'm going to substitute this in for V, I'm just going to take V out of there. Okay? I'm going to square this formula. What's 2 squared?
4.
Okay? What's pi squared? Pi squared. Okay? What's r squared?
R squared.
Okay? All right, so that's that formula squared, right? Okay, so now, am I done? I just substituted it in. I might have to do a little canceling. Would that be the reason I'm not done? Okay, so what needs to cancel here? I got an r on the bottom and an r squared on the top. Okay, so this would need to go away, and that would take care of that, right? Okay, did I just substitute a formula into another formula? Okay, so nothing too difficult. Just know that sometimes people get stuck on a question like that because they're like, I don't have enough information here, I can't do this. They forget that it's okay to substitute one formula into another to kind of shortcut that type of question. Okay? We'll work on a few where we have to do that today. Okay, so that's what this slide was all about here. Okay, so that's how we would calculate the period of the Earth, of an orbit of a satellite if we needed to. Now, different orbits. Okay, there are lots of different orbits that we put satellites in. Okay, around the Earth. The Earth's orbital area has become like a big junkyard. There's stuff everywhere. Okay, what would the period of a geosynchronous satellite be?
24 hours.
24 hours. Why?
It moves with Earth.
Right. It's geosynchronous. That means it stays over the same spot on Earth. The only way for a satellite to stay over the same spot is if it has the same rotational or orbital period as the Earth's rotational period. Otherwise, it would fall behind or get ahead. Okay? All of our GPS satellites are geosynchronous. Okay? It's really important for them to be because that's how the system works. If they were constantly moving, we would lose their signal, okay, all the time. In fact, that was a huge problem back in the 80s when satellite TV first came out. Okay? Modern satellite TV satellites, communication satellites, are geosynchronous. They stay over the same spot on Earth all the time. That way, you can receive their signal all the time. Back in the 80s, we didn't have them all geosynchronous. Some of them were in low Earth orbit, which meant you had to have a satellite dish that was not only big, but moved. Because it would find a satellite and it would track. And it would follow that satellite as it moved across the sky. When do you run into a problem? Right. It's usually Game 7, Stanley Cup final, second overtime, satellite dishes following the satellite. Satellite goes over the horizon. Now you don't have any signal. Now, satellite dish has to go back over to this horizon and try and find the next satellite coming over and track it. Okay? So you're going to be without signal for however long. You're going to miss the winning goal. Okay? Because that's how luck works. Right? And so that was kind of a major inconvenience for satellite TV. Okay? The advantage was all you had to do was buy the dish and basically it was free. Okay? Because you were basically hijacking the signal back then. Okay? Now you just get this tiny little dish on your house and pay an exorbitant sum, okay, to have it pointed at the same satellites all the time. All right? Making sense? Okay. So geosynchronous satellites have to have an orbital period of 24 hours. Okay? Other satellites, their orbital period is going to be different. The International Space Station's orbital period is something like 90 minutes. They have 18 sunrises and sunsets a day because they're whipping around the Earth really fast. Okay? But they're much lower down. All right. Now, this thing that we were talking about before, okay? When we set this up, G being M1, M2 over R squared equals M2 times V squared over R, okay? The mass of the satellite always ends up doing what? It always ends up canceling. Why? Why does the mass of the satellite not matter?
Is it because it's apparently weightless?
It's part of it. It's apparently weightless because it's falling. Do all things fall at the same rate regardless of their mass? Yeah. Okay, so it doesn't matter what I put at a certain altitude. At that altitude, it's going to fall at a certain rate regardless of its mass. So it doesn't matter how big the satellite is. At that altitude, it has to have that speed or that period in order to stay in orbit. Okay? That is independent of mass because all things fall at the same rate. Okay? That's why the mass of the satellite cancels. Okay? I could put a basketball out where the moon is and it would have to move at the same speed as the moon. Okay? Mass doesn't matter. Okay, I'm going to give you guys a little break and then we're going to look at a couple of examples here. Okay? Okay guys, I would like you to try these two satellite motion problems. Okay? They're both asking to solve for something slightly different, but they both give you enough information to solve for it. Okay? So know that yes, these are satellite questions, so they are all going to start out with the centripetal force being provided by big FG. So big G times M1 times M2 over R squared. All right? So give you a couple minutes on those. We'll see how we do. The answers are there at the bottom. I'll try and make this a little bit bigger so it's a little easier to read. All right, so on number 2, okay, we're told the speed that Miranda moves in its orbit. So we got 6.68 times 10 to the 3 meters per second. Okay. Oh, you need the mass of Uranus. Oh, sorry, it's at the bottom, right. So 8.68 times 10 to the 25 kilograms. Okay, and we're looking for the radius of the orbit. All right, so we got FC equals FG. All right, so we got mv squared over r. This is the mass of Miranda, of the moon. All right, and we've got big G times the mass of Uranus times the mass of Miranda over r squared. So we already know Miranda's mass cancels, which is good because they never told us what it was. All right, we're trying to find r. So what I would do is say, I've got to move the r squared over here, because I can't solve for r if it's on the bottom. And moving r squared over here is going to cause one of them to cancel, and that'll eliminate the r that's on the bottom. Okay, now r is where I want it to be. So now what I want to do is bring v squared over to this side by dividing both sides by it. Okay, and that should leave me with the formula for r. Okay, so r is going to be 6.67 times 10 to the minus 11 times 8.68 times 10 to the 25 divided by 6.68 times 10 to the 3 squared. Okay. Most common mistake on this question would be forgetting to square v, okay, in this. All right, so when I plug all that in, I should get 1.3 times 10 to the 8. It might be slightly off, but it shouldn't be too far off. Okay. So 6.67, second e negative 11, okay, and then 8.68 e 25, close the brackets, 6.68 e 3 squared. Okay. That looks like 1.30 times 10 to the 8 to me. Yeah? Okay. All right. Get one here where you have to do the period. Yeah, okay. So on this one here, okay, I want you, don't worry about orbital speed. I just want you to try and solve for the orbital period of the Landsat satellite. Okay? Now, it does tell you that it is orbiting at a height of 912 kilometers. Make sure you look at the diagram to see what that means for you and what you might have to do with one of the numbers you need. Okay, so we're looking now for the orbital period. Okay, you might need to do that substitution thing we talked about. Okay, so first thing we got to realize is they tell me the altitude, which is measured from the ground. I need the distance from center to center. Now, I don't know if you use the number they put up here, which is different than the number on your formula sheet. In the end, it doesn't make a huge difference. Okay, but I need to actually calculate the real orbital radius center to center. So that's going to be 912,000 meters, not kilometers, but meters, okay, plus the 6.38 times 10 to the 6 meters, okay, that's the first operation I have to do. I need to know the actual orbital radius, so 912,000, okay, plus 6.38 E6, right? Now I've got the real radius, 7.292, okay, times 10 to the 7, I believe it was, meters. Okay, is that right? 10 to the 7? No, 10 to the 6, sorry, 10 to the 6. All right, so now I've got the actual orbital radius. I know it's orbiting the Earth, so one of my givens is 5.98 times 10 to the 24. I think their number is 5.97, but probably you used your number from your formula sheet. Okay, kilograms, and I'm looking for the orbital period. All right, so FC equals FG. That is still true. Right? And that's going to mean that mv squared over r equals big G times the mass of the Earth times the mass of the satellite over r squared. Mass of the satellite's going to cancel, okay? Which is good because they never told me what it was. I want orbital period, not orbital speed. Can I substitute? Or I could find orbital speed and then do it in 2 steps. Either way would work. Okay, I like to substitute because I want to do it all in 1 step. Okay, so I'm going to say that V equals 2 pi r over t, and I'm going to substitute that squared into this formula. So I'm going to get rid of that m because I already know it's gone. Okay, 2 squared is 4, pi squared is pi squared, r squared, t squared. Okay, so now I've substituted in that formula for V. Now I need to isolate what? T. Right? T is on the bottom right now. Can I solve for it on the bottom? No. All right, I'm going to move t squared over here. All right, then I'm going to move everything else to the left. So I'm going to multiply, okay, both sides by r squared. So this r is already going to cancel. I can get rid of this r and this r. Okay, when I multiply r squared by r, what do I get? R cubed. Okay, then I'm going to divide both sides by big G times the mass of the Earth. And then what am I going to do? Square root it. Okay, so tricky manipulation for sure, right? So I'm going to have 4 pi squared times the 7.292 times 10 to the 6 cubed, okay, divided by 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24. Okay, so when I punch all that in, right, I'll have 4 pi squared, okay, times, in brackets, 7.292 E6 cubed. Okay, so that's on the top. Now I've got that number. Divide by the bottom. 6.67 E negative 11. 5.98 E24. All right, then I got to square root that number. All right. So the orbital period of that satellite is going to be 6.19 times 10 to the 3 seconds. Okay? Is it really all just algebra? I mean, other than the little trick with the radius, okay, and maybe the substitution, even the substitution is just algebra. Okay? So really, guys, like the satellite motion stuff, like once you've done a few of these, you've done them all. They're all the same. Okay, it's just a matter of you're solving for something different on every question. All right. All right, let's try those two and we'll call it a day.